My recommendation is not to try to take notes for a minute. We're just going to play around with this. We're going to hit the pause button, go back to talk matrix multiplication, and we'll swing back around to this stuff. But does anyone have a favorite animal that they would like to have pretend biology about today? Yes.
Let's just do capybaras. Why not?
Okay, cool. Help me to spell capybara.
C-A-P-Y-B-A-R-A.
Cool. Okay. So if we're talking capybaras here, I'm going to go ahead and use the letter C for the number of capybaras in our population. Now, because I have no idea how population dynamics play out for capybaras, we're just going to make some stuff up. So I'm going to think about our capybaras, and we've got a population living out there somewhere in the wild. And because I don't know much about their dynamics, I'm just going to group. Is there like a word for baby capybaras? You know how like a baby cat is a kitten? Is there like a word for a baby capybara?
I think so.
Okay, so I'm just going to think of our capybaras as like, we've got the babies, we've got the juveniles, and we've got the adults. So those are like my three categories of capybaras here. Cool. How many babies do we want in our population? We're just making stuff up. 100? Okay. How many juveniles are going to be out there in our capybara population? We're really just making stuff up. Cool. And in order to take care of that many babies, I think we need a whole lot of adults. Maybe? I don't know. So let's say we've got at least 50 adults to handle all those babies. So that's kind of where we're starting with that distribution. Now, they're out there in the wild. So a couple things are going to happen. Capybaras are going to have more babies. And sadly, out there in the wild, some of the capybaras are not going to survive. So let's make some assumptions here. Let's make the assumption that capybara babies cannot have babies. There's some amount of reproductive maturity that they have to reach. And let's say that our juveniles, some of them are reproductively viable, but they're not very good parents. That's just going to be our reality here. So on average, how many, for each female juvenile capybara, on average, how many offspring do you think they're going to have? I'm thinking some number less than one, right? Like some of them are going to have babies, but not everybody, and they're not going to be reproductively viable. So I'm going to say that we're going to get, I don't know, I'm really making stuff up here, 0.8 babies from each juvenile. Do we know, do capybaras have multiple offspring in I'm going to call it a litter because I don't know what else to call it. We're doing some research. Thank you, internet. Because if they don't, then I'm going to lower that number. Dun, dun, dun. We can also just make it up.
4 to 5.
4 to 5. Okay, so we're going to say that our adults have 4 babies. From each adult. Now, I said that there was something else that was going to happen, and sadly, living out there in the wilds, some of them are going to die. Disease, predation. habitat loss. So if we think about from one breeding cycle to the next, maybe only 50% of our babies survive. Our juveniles, they're a little faster, a little stronger immune systems. Maybe nearly all of our juveniles survive. Now, some of our adults, they're getting old. 70% of our adults survive. Now, I just completely made all this stuff up, but we made enough of it up that we can now think about what's going to happen to this population over time. So now comes the fun with the diagrams. So I'm going to label my diagrams as our babies, our juveniles, and our adults. So our babies don't make more babies, but our juveniles do make more babies. So if I think about what's going to happen at the end of that breeding cycle, the number of juveniles we have is going to have an impact on the number of babies we have in the future. And for each of those juveniles, I'm going to end up with 0.8 babies. So I'm going to write that as 0.8J because I'm going to do 0.8 times the number of juveniles we had. Now our adults, they're also going to have babies. So our adults are also going to feed into the number of babies we have for the next breeding cycle. So I'm going to write that as 4A. Now, for the fun part, or the sad part, we're going to assume that babies grow up to be juveniles and juveniles grow up to be adults. But not all of our babies are going to grow up to be juveniles. In fact, only 50% of those babies are going to grow up to be juveniles. And our juveniles are going to grow up to be adults, but only 90% of our juveniles are going to grow up to be adults. Now, juveniles can't go backward in time and become babies, just like adults, even if they might want to, cannot go backward in time and become juveniles again. So those 70% of adults that survive, they're feeding back into the adult population. Now I'm going to add the growth subscripts. So this is going back to stuff we did in 17A and those recursive notation sequences to figure out how many babies I have one time step into the future. I need to look at what's happening at the current time step. Same thing with my juveniles. Same thing with my adults. A sub T. Okay, so we're going to actually run this mechanism based on the things that we came up with and our initial conditions to look at one breeding cycle into the future, how many babies, juveniles, and adults we have. So let's run our system. Okay, so let's look at the babies first. These 100 babies, they're moving on to be juveniles, but my new babies, I really didn't leave myself enough space here, but that's okay. So my new baby population, meaning the arrows that are feeding in, are going to come from 0.8 times my juveniles. So 0.8 times my 60 juveniles plus 4 times my adults. Oh, I ought to be able to do this. 6 times 8 is 48. So 48 plus 200, so that's 248. Now we can look at our juvenile population. So the only thing feeding into our juvenile population is that half of our babies are going to grow up to be juveniles. So I've got 0.5 times 100. So I've now got 50 juveniles. And because I'm a little bit short on space, I'm going to write in my adults up here. So my adult population, I've got the juveniles that are growing up. So 0.9 times my 60 juveniles, and 70% of my adults are going to survive. Cool. I should be able to do all that math quickly in my head, but that's just not how my day is going. So 0.9 times 60 plus 0.7 times 50. I'm looking at 89. Now you can imagine that some researcher, some modeler would really like to know, okay, if those dynamics stay the same and this keeps circulating in there, what are those populations going to look like after a really long time? And it turns out that writing out each step like this is kind of tedious. And also, it turns out that if we're trying to look ahead to the future, what's going to happen after a really long time? I'm going to throw out words from 17A. We're looking to see if eventually we're going to settle into some fixed point of a population distribution, or using words from 17B, we're going to be looking for that equilibrium state for how that population distribution is looking. Okay, so I'm going to take those equations, try to remember everything that's on there, and flip the page. Oh wait, I don't have to. Oh, cool. I can cheat. I can look at it while it's up here. Yay. I'm just going to have to hold it so that it's not like at some weird angle, but all good. Okay. So I'll try to get that lined up. So if I take those equations that I just had, and I'm going to write them backwards for a reason. So for my, we started off with our babies, our juveniles, and our adults. Yep, I'm writing it as a vector, looking like 100, 60, 50. And when I got the next, in order to get that next population, or A sub t plus 1, or rather, sorry, I didn't mean to put my adults first. My adults were last up there. The way that we got our next population of babies, juveniles, and adults, if I think about that as like we had it as 3 separate equations, to get next year's babies, I had 0 times this year's babies plus 0.8 times this year's juveniles plus 4 times this year's adults. To get next year's juveniles, I had 0.5 times this year's babies, and then all of the juveniles had to grow up and none of the adults could go backward in time. To get the next year of adults, my babies can't skip being juveniles. I had 90% of those juveniles grow up, and I had 70% of those adults live. And there's a convenient matrixy way to write this, which is to say that all of that can actually be written as a matrix times that initial population vector that we had. I keep putting the A first, and I think it's because it comes first in the alphabet. And I can write this matrix like this. So the whole reason that we're doing matrix multiplication and matrix addition and subtraction and all of this stuff in homework 18 and kind of laying that foundation is actually because we want to be able to use it as a fast tool to look at population dynamics. So let's go backward in time and actually do some matrix multiplication practice. So a couple of things that we should know about matrices. Even if you've never really worked with matrices before, if you have done anything at all in like Excel or Google Sheets, you've secretly been working with matrices, and the way that we label matrices is kind of similar to how cells are labeled in Excel. So if I have some cool matrix, I'm just making up numbers, 3, 2, -1, 1. We talk about this matrix, the size of the matrix or the dimensions of the matrix. I have 2 rows and 2 columns. So rows are always horizontal, columns are always vertical. And I remember it just by thinking about, like, if I have columns that are holding up a roof, the columns are the vertical part. So this has 2 rows and 2 columns, and we can label each piece in here based on what row and what column it's in. So that's column 1, column 2, row 1, row 2. I learned this as all matrices are Roman Catholic. Sometimes I've heard it as matrices like RC Cola. Whatever you need to do to remember that the dimension for the row comes before the dimension for the column. So this one happens to be a 2 by 2. But let's say I have another matrix B, and my matrix B is 0, 1, 2, -3, 4, 5. This is 2 rows by 3 columns. So that is a 2 by 3 matrix when we talk about the dimension. If I'm going to add matrices together, they have to have exactly the same size. So I cannot add A to B. But if I had another matrix C that was 1, 0, 4, 7, then adding A plus C would look like doing addition in each spot where it goes. So in the row 1, column 1 spot, I would add those 2 values together. So I would have 1 plus 3. In the row 1, column 2 spot, I would add the values in row 1, column 2, and keep going. So I would have the row 2, column 1 spot added together, and the row 2, column 2 spots added together. And my result for A plus C would be 4, 2, 3, 8. Not super exciting. It's really mostly just arithmetic. But it is important to kind of have that skill down. By the way, if you are someone who generally relies on a calculator to do arithmetic, there's really no way around that once we get to matrices, because the only way to do these problems is to actually do the arithmetic part. And so that is actually what you're getting tested on the quiz. So just make sure you've got those addition and multiplication facts like rolling off the top of your head. Okay. I want to talk multiplication for a second, or maybe for more than a second, and do an example with multiplication. And I'm going to use up a lot of space, and that's okay. So I want to multiply A times B. So I've got 3, 2, -1, 1 times 0, 1, 2, -3, 4, 5. So I want to talk briefly about multiplication. And in order for matrix multiplication to be defined, in order for it to work, you've got to have the right dimensions between the things that I'm multiplying. So this one right here is a 2 by 2 matrix. And this one over here is 2 by 3. Again, that's because my rows come before my columns. So I've got 2 rows, but 3 columns here. And when I go to multiply, I have to make sure that those inner dimensions are the same. And the outside dimensions are going to tell me the size of the answer. So when I go to multiply matrices, especially at the beginning, once you get faster, you won't have to do it this way. But I'm going to give myself lots of space over here because I need to make room for a 2 by 3 matrix. And I'm just going to actually give myself spots to put arithmetic in. I hope that's big enough. Now, part of the reason that I do this, especially for the first couple, if this is your first time seeing matrix multiplication, I think it's really helpful to label where the spots are. So this is row 1, column 1, row 1, column 2, row 1, column 3, row 2, column 1, row 2, column 2, and row 2, column 3. And what labeling them that way lets me do is to know what's going in there. Rows always come before columns. So what goes in here is row 1 from the first matrix times column 1 from the second matrix. And we treat it kind of like we do for a dot product. First pieces match up multiplied, and then we add that to second pieces matched up multiplied. So row 1 times column 1 is going to look like 3 times 0 plus 2 times -3. So 3 times 0 plus 2 times -3. My next one needs to be row 1, column 2. So I'm going to have 3 times 1 plus 2 times 4. And then I'll still have that 3, but now I'm times the last column. So 3 times 2 plus 2 times 5. You do not have to write any of this out. You can totally do the arithmetic in your head. You can jump straight to the final answer. Everyone will be totally fine with that. I'm doing it just because it's the first multiplication problem we're doing. So now I'm only going to be focused on row 2. So row 2 times column 1, I would have -1 times 0 plus 1 times -3. And then -1 times +1 plus 1 times 4. And then -1 times 2 plus 1 times 5. And if I cleaned all of that up, then my result of A times B would look like 0, let's see, that's -6. 3 plus 8 is 11. 6 plus 10 is 16. -3. -1 plus 4 is a +3. -2 plus 5 is also a +3. Is that what anyone else got? Did I get my arithmetic right? Okay. So it's not difficult. It's sometimes challenging to keep track of and making sure that you're getting everything in the right space. But what you're actually doing does come down to arithmetic when we're multiplying matrices. More of the time in this class, we're going to spend more time multiplying a matrix times a vector. That's going to be true both this quarter and next quarter. So I want to get some practice with a matrix times a vector. I'm going to flip a page. So I'll just make up new matrices so that I don't have to flip my page back over. So there's my matrix A. And if I had a vector, one, one, two, I've got these two things. And if I want to multiply them together, I've got to do a quick check to see this is a 3 by 3. This is a 3 by 1. So my inner dimensions match. So that's good. And my outside dimensions are going to give me the answer. So it is possible to do this matrix multiplication. And I'm going to. So my A times X. Again, my inside dimensions match. My outside tells me the answer size. So my final answer is a 3 by 1. So I'm just going to give myself a little bit of space here. I'm going to let you all try that matrix multiplication. So first row times the only column we've got, second row times the only column we've got, and then third row times the only column we've got. I'm going to do it too, and we'll see if we get the same answer. I got 933. Yeah. Sweet. Okay. I was just taking a look at homework 18, since I know for those of you that have the quiz today, folks might be wondering about homework 13. One other thing that is on homework 13, notation wise, is transposes. So let's talk about a transpose. And also, I want to briefly go back to thinking about dot product between vectors. So we actually have an option when we think about vectors kind of as matrices. Matrices. I can think about them as column vectors or as row vectors. So if I had two vectors, and I'm going to keep them just, if I go back to the notation we had on the previous assignment, and if I just had the vector like 1, 2, and a vector 3, -1. If I'm thinking about those two vectors and I wanted to think about them as row vectors or column vectors, if I made each of these a column vector, I can't multiply those together because that's a 2 by 1 and that's a 2 by 1, and those inner dimensions don't match. So when I conceive of a vector as either a row or column vector, it turns out that we end up with two options for multiplication. I can either dump the first vector on its side or the second vector on its side. So if I dump the first vector on its side, I'm technically taking the transpose. So if that's my u vector, the transpose of u trades rows for columns, or columns for rows, depending on how you want to think about it. But it takes that vector and turns it into the row vector 1, 2. This is now a 1 by 2. So if I think about my v remaining as a 2 by 1, then my inner dimensions match and the outside tells me the size. And that outer dimension there, that 1 by 1, that's a scalar. It's just a number. So if I have my u dot v and they're both vectors that are column vectors, taking the dot product is equivalent to multiplying u transpose times v. Yeah.
Is that a quick question about the above matrix?
Yeah.
Why did 2 + 1 + 6?
I don't know, maybe I made a mistake.
I was wondering.
So I'm taking my first row times the column. So I'd have 2 times 1 plus 1 times 1 plus 3 times 2.
Oh.
So I think I got it. Yeah. If I take the transpose of something bigger than just a vector, let's say I had a B matrix and my matrix was 1, 2, 3, 0, -1, -1, sure. And I take B transpose. That means each row now becomes a column. So my first row becomes my first column. My second row becomes my second column. My third row becomes my third column. I think about it as like, I don't know, it fell over and flipped around. I said I would leave space in case people had questions about homework 18. So I've got homework 18 pulled up. I don't know if there are any questions that anybody wants me to go over. And if not, that's okay. There's not a whole lot to homework 18, kind of like, there's actually not a whole lot to homework 17 either. It's a lot of just mechanically doing stuff.
I have a question about homework 9.
Sure. Since no one's asking questions about homework 18, let's move into some word problems. Okay, I've got homework 19 pulled up.
So for 2B,
Mm-hmm.
like it's talking about the drug being like getting diffused into the bloodstream, and then I was wondering how you know that like the percent, like the other half of the percentages like stay in the system, like they loop around rather than just,
So so I'm going to hold that thought. Let me pull this up on the screen, maybe. Just so that we're all looking at the same thing. Come on, wake up. Let's send to display 1 and zoom in a little bit. Okay, so we're looking at 2B there. So, and sorry, I've got 2 different screens trying to manage what Zoom folks are seeing. Let's try that. Okay. So a drug taken orally eventually diffuses from the stomach into the bloodstream. At each time step, 50% of the drug is absorbed from the stomach into the bloodstream, and 80% of the drug in the bloodstream is metabolized. So if we're not accounting for something else happening to it, it's stuck where it is. So this is a little bit different than if we're talking about population dynamics, where we know that each population has to move into the next age category. Here, we've got something sitting in the stomach. If 50% of it is moving to the bloodstream, what's the other 50% doing, right? So it's a totally oversimplified problem, but based on the language in the problem, it's stuck there. So we've got stomach, bloodstream, leaves entirely. Yeah, I don't know if that is a satisfying answer or not.
yeah, I think I understand now because there's like nowhere else for it to go. So
Yeah.
that's-
Yeah.
And then for question 1.
Yeah,
So I just want to make sure that this was correct, but so like a row or a column of zeros, so it means like that those factors are not contributing to that, like the next time interval or something.
sure. Let's take a look at what happens when we've got a row or a column of zeros. I think that's a good one to take a look at. So let me switch back over. Have some fun here. Too many buttons to hit to move things, but okay, so let's say that I'm just going to go back to my babies, juveniles, adults. We'll just go back to our capybaras and let's see what happens if we give ourselves a row or a column of zeros somewhere. So I'm going to start with what we had and then we'll modify it. Only I need someone to help me remember what we had. This is 0.5. Okay. I was like, I don't remember. 0.5, 9, and then 0.7?
Zero.
Okay. Oh, right, 0.9 and then 0.7? Okay. And then that was getting multiplied by my babies, my juveniles, and my adults. So if I had, let's say that I switched the second row to be all zeros. So that this was 0.8 for 0, 0, 0, 0.9.7. And I'm just going to write this. I'm going to ditch the subscripts and just write this as BJA for myself. So if I were to look at this multiplication, I've got 0B plus 0.8J plus 0.7A. And that's really what's going to give me my next population of babies. And now when I look at the second row, I've got 0B plus 0J plus 0A, which actually told me that there are no juveniles in the next breeding cycle. It's like, yeah, whatever. Yeah, that's really gonna bother me. Cycle. There we go. There are none in that next breeding cycle. So having a row of zeros is changing like one of the outcomes for the populations. Now, what happens if I have a column of zeros? So let's say I made the third column zeros. And I were multiplying that out. So now I'm looking at 0B plus 0.8J plus 0A and 0.5B plus 0J plus 0A and 0B plus 0.9J plus 0A. Now here, what that's saying is one of my inputs is totally ignored. That one of my inputs has no impact. So if we've got a 0 in a row, it's saying like one of my outputs is going to be 0. But if I have a 0 in a column, it's saying one of my inputs doesn't affect the final result. So you're right that like each one is saying something is kind of not being taken into account, but if it's a row or a column, changes what the thing is that's not having an impact. Other questions from homeworks 17, 18, 19? Yeah. Sure. So let me pull that back up. Come on, wake up. Okay. D. By the way, if you are not looking at the textbook, that's fine, but he did pull each of these from the textbook. So they are textbook problems. He wasn't making stuff up. So here we've got a population of spotted owls, and our owls have been divided into juveniles, subadults, and adults. So I'm going to call those juveniles, subadults, and adults. And we know some things about the population dynamics. And I'm going to draw a diagram and then think about what the matrix looks like. And I can't remember on the homework if he specifically asked you to draw the diagram. Yeah, you have to do the diagram and the matrix. Cool. That's what I was going to do anyway. I'm going to scoop my juveniles over just a little bit. So I've got my juveniles, my subadults, and the adults. So when it says 60% of juveniles survive to become adults, that means my juvenile population is moving into that subadult group at 60% of J, or 0.6 times J. And 70% of our subadults survive to become adults. So that's 0.7 S. And 94% of our adults survive the next year. So 94% cycle back into my pool of adults. And assume that adults produce on average 0.33 juveniles each year. So it didn't tell us that subadults produce juveniles, which means we're going to assume they don't. We shouldn't assume anything that's not explicitly stated in the problem. So the only thing I know now is that adults are going to produce juveniles at 0.33 times the adult population. So when I'm putting all of that together, you can decide to do the intermediate step of writing it in equations and then going to the matrix. And maybe the first couple are going to be nice to do that way, or you can go straight into the matrix. I'm going to go ahead and do this as equations and then the matrix. So I'm going to have my juveniles next year, my subadults next year, my adults next year. I don't know why I chose N and not T, but I already started writing it this way, so I'm just sticking with it. So the only input on my juveniles is from the adults. So for completeness, I'm going to write this as 0 times my juveniles now, plus 0 times my subadults now, plus 0.33 times my adults now. For my subadults, the only input is from the juveniles. So I've got 0.6 times the juveniles. Now, unlike that problem where we had drugs in our system, we have to, when we've got population dynamics like this, we assume that everybody gets pushed forward. Nobody gets to stay in the same age class. So if everybody gets pushed forward, then none of those subadults remain subadults, and none of my adults get to go backward in time. For my adult population inputs, my juveniles don't get to skip subadulthood, but 0.7 of my subadults, or 70% of my subadults, do survive. And in terms of my adults, 94% of them survive. So if I write this as a matrix equation, that's going to look like 0, 0, 0.33, 0.6, 0, 0, 0, 0.7, 0.94 times my current populations are going to give me my future populations. Yeah.
Why do we write juvenile plus 1 and like sub adults with like SN plus 1? Why do we write it?
So this is the notation that we had in 17A for recursive sequences. So the textbook is just like keeping that same notation for recursive. And sometimes I see it with an N and sometimes I see it with a T, but either way, it's that idea of this recursive notation that I get the next population based on the current population.
So it's like technically a recursive sequence?
It is.
Okay.
It is entirely a recursive sequence. And where we're headed is to look for what fixed points of a recursive sequence look like when it's actually defined as matrix multiplication. That's where we're headed. Because, and here's the reason that it's like recursive, or one reason we could think about it as recursive. So if I gave us an initial population we would do this multiplication and then we would know what the population was at time t equals 1. Well, to get the population at t equals 2, I do the matrix times that new population I just got. And then to get it at time 3, I do that matrix times that new thing I just got. And so we end up like kind of stacking up the matrices together. So if I wanted to know my population 5 years into the future, we would have ended up multiplying this matrix 5 times my whatever that initial population was. S1, A1 would give you your population 5 years into the future. I probably meant to make those zeros and not ones. So what we're building towards is like faster ways to multiply matrices together really quick, or at least to know kind of what's going to happen when I multiply a matrix together a bunch of times. Which we got a little sneak preview of on homework 18, because he gave us some really special matrices in homework 18, where when you do the matrix multiplication, nice things happen. Okay. We've got a lot of time left. What else do we want more practice with? Or do we want to see previews of things to come? Yeah. So can I ask, is it words to diagram or diagram to matrix? Which is the harder part?
I think it's like words to diagram.
Okay. So then I'm going to make up something. Sure, we can do A. So we've got a population of yellow perch, which are a freshwater fish, lives to a maximum age of 4 years. And in this problem, we're defining ages as age 1, 2, 3, 4. Now, I haven't really even read the whole sentence. I am just looking at, just like visually, the things that pop out, things that I'm throwing my pen at, the things that pop out to me are, I'm looking this and I'm looking at age 1, 2, 3, 4. So I'm going to go ahead and start my diagram, right? And I need age 1, 2, 3, and 4. I don't know what to call those. So I'm just going to call them 1, 2, 3, and 4 for now. So those are my populations. Now I need to know what happens. So reading through this in order, it says they live to a maximum age of 4 years. Well, that means I'm not going to have 4 cycling back into itself, because none of my 4-year-olds are going to still be alive. So that's it. Now, 5% of age 1 individuals survive to age 2. So coming out of 1, I'm only going to have 5% moving that direction. So I'm going to call that 0.05. Now, I'm already in trouble because I normally would say times something, and I don't want to use numbers for my times something. So it sounded good, but I think I'm going to switch these to be A, B, C, and D. It's totally your choice what you put in here. But I'm just going to remind myself those are 1-year-olds, 2-year-olds, 3-year-olds, and 4-year-olds. So 5% of my 1-year-olds live to be 2-year-olds. Now 20% of my 2-year-olds survive to be age 3. So I've got 20% moving this way. 75% survive to be age 4. both my age 3 and age 4 reproduce, creating age 1 offspring. So my age 3 dump back into age 1, and my age 4 dump back into age 1. So my age 1s get 100 new babies from each of my age 3s, and my age 1s get 150 new babies from each of my age 4s. If you can make the diagram, you can do the next part. Now, is it faster to go straight to the matrix? Yes. But if, as you're just getting started, if you want more practice, I think an easier starting point, for me anyway, is to write the equations first. Or at least to think about writing those equations, and just remember that I want to keep, for the matrix, I want to keep all of the pieces. So my rows have to be in terms of what's A contributing, B contributing, C contributing, D contributing. And then, so my rows are like the outputs and my columns are the inputs. So A does not contribute back to A. Babies don't have babies. B does not contribute back to A either. C does though. And so does D. So I'm looking at 0, 0, 100, 150. Now my second row is my output for my age 2s. My columns are my inputs. So my A inputs 0.05 to age 2. That's the only input to age 2. So I know the rest of this row is 0.
Could you like rewind on that? I didn't fully understand.
Yeah. So none of my age 2 fish get to stay age 2. So when I'm thinking about this matrix, each row is telling me what's happening next year. So my next year age 2 fish are coming from my this year age 1 fish. If I look at the diagram, I'm literally just looking for any arrows that are pointed into that bubble. There's only one arrow that points into that bubble. So to get next year's fish, I look at 5% of the age 1 fish, but all the age 2 fish have moved on. And none of the age 3 fish can go back and become younger. And none of the age 4 fish can go back and become younger. I think it's easier to think about the equation first and then try to do the matrix. So when I think about my age 3 fish, there's only one input. So none of my age 1 fish get to skip being age 2. 20% of my age 2 fish grow up to be age 3. None of my age 3 get to stay age 3, and none of my age 4 get to go back in time. 0.200. For my age 4, I have no input from age 1, no input from age 2. I do have an input from age 3, but I have no input from age 4 because we said that all of our age 4 fish are going to die. By the way, this is a Leslie matrix. Has a special name if we are specifically talking about female population, and every population moves to the next age class, and in the top age class, they age out or die out. We have a special word for the values in this first row, and that's the fundity. It's in the textbook. You don't need to know it, but maybe it comes up in biology. I don't know. The fundity is the average number of female offspring produced by each female. So cool word. I don't know. Yeah.
Can we go back to the warm-up problem?
Yeah, totally. Let's
So,
go back to the warm-up
yeah.
problem.
I know I asked you for like the.
Hmm.
I like kind of forgot, so how did you get to the 3 pi? Like using the.
Yeah, so I have to, if I ignore the plus or minus, the 1 over root 2 or the root 2 over 2, knowing that it's pi over 4, that part we have to memorize. The knowing that my battery's about to die, by the way, so folks on Zoom are probably about to lose me. But for the how I know it's 3 pi over 4, I don't have to like have the whole unit circle memorized, but I do need to know that if this is 0 and this is pi, cosine is negative over here. So I know that if that's supposed to be negative, I've got to grab the value from over here. And the value from over there, I'm going to get by thinking about that pi as 4 pi over 4, so that it's got the same denominator as what I'm looking at. And then I'm going to say, okay, if I've got to be over here, I'm just going to back off a pi over 4. So if this is 4 pi over 4, then backing off, I'm at 3 pi over 4. It's not the only way to think about it, but that is how I think about it.
Oh, wait, so how did you know that cosine is negative in that quadrant?
So cosine corresponds to like the x values. So all of the x values are negative over here. The other trick that sometimes we learn in like a trig class, all students take calculus. Sorry, that's not showing up very well. Try a different color. All students take calculus. So that's which functions are positive in each of the quadrants. Everybody's positive in quadrant 1, only sine is positive in quadrant 2, only tangent is positive in quadrant 3, and only cosine is positive down here. But when it comes to thinking about dot product and the angle between two vectors, we're only living on the top. We're only talking about between 0 and pi.